distinguished guests, ladies and gentlemen from 5 continents and 20 countries. Welcome to 11th Nano-Satellite Symposium, 8th Global Meeting and Preliminary Workshop for the 8th Mission Idea Contest. We are honored to host the activities jointly organized with UNICEF Global with the support of the International Academy of Astronautics. Over the last 2 decades, small satellites have been a disruptive technology changing the economics of space and forming the new space industry. Particularly with the CubeSats, any country can now venture into developing space technology and can have a presence in space. Many new private initiatives have been formed and started to lead space technology, producing space assets in short time with affordable budgets. As a result, constellation of satellites achieved increasing temporal resolution, leading to a wealth of information collected from space. Large LEO communication, internet constellations, XR, and IoT systems have been developed for continuous communications and Earth observation in all conditions. The 11th Nano-Satellite Symposium, which is held for the first time outside of Japan, together with UNIGLO and PREMIC, will present and discuss all these developments taking place worldwide and in Turkey. Istanbul Technical University is the first technical university of Turkey, and it's identified with the education of engineering and architecture. In 2023, when the Republic of Turkey will reach its 100th anniversary, we will be celebrating 215th anniversary of our university. Undoubtedly, this historical intersection is a source of pride and pride for us. Our university has played an extremely significant role in the development of Turkey, from education to science, technology to industry, sports to art and politics. We will continue to pioneer technological investigations and transform the future. Our ITU Space System Design and Test Lab is the leading research and development institution in Turkey for nanosatellites since 2005. Our university also supports small industry efforts in Turkey. Turkey currently has 7 CubeSats in orbit, all involving the efforts of ITU. We are proud and will continue strongly support efforts in the field. As a president of ITU, I welcome you to the meetings and wish you all fruitful and successful events. I thank you for coming and greet you all with respect. Thank you very much.
Okay, now we will have a 5-minute break before we start with the keynote talks. Thank you. Hopefully, we'll be doing so for the rest of the meetings. Today, we have two, I think, great keynote talks. The first one is by Professor Shinichi Nakasuka of University of Tokyo, entitled Recent Japanese Activities of Micro-Nano-Satellites and Their Applications to Business in the World. Professor Nakasuka graduated from University of Tokyo and received his PhD in 1988. He joined IBM, and then he has been working for Department of Aeronautics and Astronautics in University of Tokyo, and as a full professor since 2004. He is the former chairperson of UFAC, Aerospace Technical Committee, and has been the chairperson of UNICE Global since its beginning in 2013. His major research areas include micro-nano picosatellites, autonomy and intelligence for space systems, novel space systems, and guidance, navigation, and control of spacecraft. He developed and launched 13 micro-nano picosatellites successfully, including the world's first CubeSat launch in 2003. He contributed to establishment of several space startups and to the space education to ASEAN and many other countries. He is also a member of Japanese government to steer the governmental space activities, and very recently, he was awarded the Frank J. Malina Astronautics Medal at the International Astronautical Congress back in September this year. Please welcome Professor Nakasuka to deliver our first keynote.
So, thank you very much, Rustam, for your very kind introduction. And hello again. My name is Shinichi Nakasuka from University of Tokyo. Today, I'd like to show you the recent activities of Japanese universities and also the business in the world. And let me start how the micro-nano satellite is important as a low-cost and affordable space asset. Maybe as you know, since around 2000, a very big game change has been performed by micro-nano satellite. And the initial satellite was launched by ourselves, Sci4 1U CubeSat. And starting from that, as you see that the many type of the application have been appearing, including the remote sensing, telescope, bioengineering or re-entry experiment, communication, space science and exploration, and even the high resolution, like a 1 meter resolution would be possible using the 100 kilogram satellite. And the active players have been the universities or venture company from universities, but recently the government think that this is very important too, and start investment, a very big investment to this area, like the United States, European countries, China, and so on. Unfortunately, Japan is behind that, but recently they start investment. And so this showed the number of satellites less than 50 kilogram launched per year. Maybe as you see, more than 500 satellites will be launched from now on. Of course, we should be careful about the debris mitigation, but this kind of the very big number of the small satellites will be launched. Let me show you our first success of the 1E CubeSat in 2003. Two universities in Japan, our university and the Tokyo Institute of Technology, succeeded in the development on the launching of the world's first CubeSat in 2003. At the time, we didn't have much money, so we should develop the satellite within just $30K US. And we expect them to survive in space for about 6 months, but fortunately, it has been surviving space for more than 19 years. And not only the satellite development, but we could obtain various experiences and skills, including the ground operation, frequency acquisition, and so on. So this was the start of the micro-nano picosatellite world. We didn't start this kind of activity from first. Initially, we started the paperwork contest called the Satellite Design Contest in 1993. And we started the United States and the Japan collaborative program called the USSS University Space System Symposium in 1998. So this is a very unique symposium. Several universities from Japan and the United States get together at Hawaii to discuss what kind of the practical project that can be performed by these universities. And I was many times asked by why you had this conference in Hawaii. We are saying that Hawaii is a midpoint between Japan and the US. Every time I enjoyed visiting Hawaii. And within this symposium, the concept of the CANSAT and the CubeSat appear. And many universities in Japan has been focusing on that. Sorry. And then we successfully launched the world first CubeSat in 2002. And UNISEC was founded in 2002, maybe at the same era the CubeSat has been developed. So now, based on the success of this satellite, many universities are performing their own various projects. So this is the current situation of Japan. The important thing is that we did not start from the CubeSat development. We started from the design contest and the CANSAT and the CubeSat. So this shows our university's history of the nano-satellite development. We started the world first CubeSat in 2003, and the second CubeSat was also the one-year CubeSat. And we challenged the space science with the National Astronomical Observatory of Japan in Nano-Jasmine. And the Hodoyoshi 134 were Earth observation satellite. And the Tricom 1R and the ACT-D was a technology demonstration satellite. Also, we have been supporting the foreign country to develop a satellite, which is a capacity building support program for Vietnam, Micro Dragon, and Rwanda, RuaSat-1. And also we challenged the deep space exploration with Procyon and Aquarius. And now we are developing the 6U CubeSat together with the student and the venture company. In total, we have been launching successfully 13 satellites, and now we are waiting for the 4 satellites more. And more than 120 students have been trained in this kind of the project. Let me show our first satellite, Psi-4. It is very, very simple mission, a Pico bus technology demonstration in space, because at the time there are no such kind of the small satellite proven in space. And in addition to that, we have a small camera which could take a picture like this. And after the 3 experimental satellites, we started the practical or business satellite development project called the Hodoyoshi project in 2010. I was the leader, and I collaborated with more than 10 universities and more than 170 small industries in Japan to create a certain infrastructure of the microsatellite development within Japan. We developed the 4 satellites, Hodoyoshi 1 through 4. Not only that, we created several miniature or advanced components suitable for 50-kilogram satellite. And we established ground infrastructure like a ground station and a ground testing facility. And it created several new missions. Especially, we focus on the reliability concept suitable for 50-kilogram satellite. This is the meaning of Hodoyoshi. Hodoyoshi is a Japanese word, stands for something like a just good or good enough. That means not too much. Okay, so this is a very, very important concept. In total, we'd like to create a new paradigm of space development and utilizations based on 50-kilogram satellite. And let me show the several satellites and pictures taken by the satellite. So this is Hodoyoshi 3 and 4 developed within our building. And we made a restriction that the satellite should be developed within 3 million and 2 years. And we successfully did it. And this satellite has a very good capability as an Earth observation satellite as well as space science satellite. So these are some of the pictures taken by the satellite. So this is the lowest resolution camera. So another one. And the 24-meter resolution camera could take this kind of the picture. And the highest resolution, 6-meter camera, resolution camera could take this kind of the picture. Maybe as you see, the rice field or agricultural field can be recognized by one. So we can detect, for example, lack of the water or some diseases. And during the mountainside, we can detect a landslide or other, a natural disaster. So important thing is that not only using this kind of the satellite alone, but make a constellation of this kind of the satellite. Big satellite can, get a very good picture of the Earth, but if we launch only one satellite can, monitor each area once per 20 days or 40 days. That is not enough. So we launch this kind of the satellite in many, and the constellation would be a very, very important technology. Also, the University of Japan have been contributing to the space science in this way. So this is a category of the size and who will be the players, main players. More than 500 kilogram or 150 kilogram, JAXA, Space Agency, has been the main player, and they have a very good records of the successful space exploration and science mission like Hayabusa 1 and 2. From 20 kilogram to 100 kilogram, JAXA and also the university have been the main player. For example, we have been developing the Nano-Jasmine, and we succeeded in the Procyon deep space exploration mission. Less than 20 kilogram, that is a nano-satellite region, universities have been the main player. And the CUTE 1.7 developed by the Tokyo Institute of Technology very successfully, and the exploration mission is now waiting for the launch by Aquarius. And as I said, the Procyon was the world's first 50 kilogram class deep space probe launched in 2014 together with Hayabusa 2. We developed within just 14 months, very, very short development time, because we can utilize the result of the Hodoyoshi project. It succeeded in deep space, several guidance, navigation, and control mission and communication missions, and also it could obtain several scientific results, like capturing of the emission of the hydrogen from the Earth and some comets. And now we are waiting for the launch of this another 6U satellite called the Aquarius. The target of this Aquarius is the other side of the moon, Earth-Moon Lagrange point 2. And it will be launched very soon on board of the NASA SLS rocket. As you know, the SLS launch has been delayed, and maybe we can expect the launch within October or November. Maybe as you see, the many components and the parts have been packed into a small area. This is the Japanese style. So Japan is very good at making this kind of packing into the small space. Do you know why? Because we are living in a small house. That is very, very important. So we are very good at thinking how to make this kind of a small space effectively. So this is Aquarius, and please watch the behavior of the Aquarius in near future. Not only Japan, of course, as I said, the United States has been investing a lot of money into the deep space using the small satellite. JPL CubeSat initiative is trying to make a series of the 3 or 6 CubeSat to the Mars, Jupiter, and so on. And we also thinking to utilize the micro satellite to make this kind of the formation flying mission. So formation flying means several satellites collaboratively conduct a certain observation missions with higher resolution and so on. For example, in this Sirius mission, we launched 3 satellites, 1 mother satellite and 2 daughter satellites. And the light coming from the target body will be reflected at the daughter satellite to be converged to the mother satellite. And we can make an interferometric observation. And then we can obtain the high resolution, even using a small satellite. So this kind of utilization of the microsatellite would be very, very important into the future. And also we are studying like this, formation flying synthetic aperture telescope in the geosynchronous orbit. Maybe as you see, the light will be reflected at the 6 mirror satellite converged into the 1 mother satellite. And then we can obtain the virtual aperture, a very large aperture in the space, like several tens of meters and so on, in order to obtain the high resolution. So this is another very important study in our laboratory as to the formation flying. So as you know, that Premic 8 will focus on the formation flying mission. So I'd like to tell you more in that session. Another university is also working very hard together with a foreign country. So this is an activity of the Hokkaido and the Tohoku University. They have been collaborating with the Philippines University to develop. This is the Diwata 1 and 2, which is Earth observation satellite. And based on the success of these two satellites, Philippines started the space agency. Okay? So it goes without saying that this kind of the micro-nano satellite has been very big significance as to the education. So because it can provide the student with a practical training of whole cycle of the space project, starting from mission conceptualization, satellite design, fabrication, and so on. The student can experience all the activities. That is very, very important. And also it is very important as engineering education because the student can get the feedback from the real world, not the simulated world, from the real world. That is very, very important. And it is very important that the education of the project management. There are 4 very important management tasks. Please guess what? Maybe time, cost, human resource, and risk. So there are 4 very, very important management tasks. And the student can learn how to manage these important tasks by, for example, sometimes making failures and so on. So from my experiences, the effect were found more than expected, and also it contributes to other technological areas. And let me show some technological aspect of the small satellite. Satellite key system technology is a non-repairable system. Once you launch your satellite, you cannot contact your satellite, even if it fails. This is a very, very severe point of the space technology. Okay? So we should make the satellite very, very die-hard, very strong against failures. For example, in our first satellite, that is just a 10 centimeter cubic 1E CubeSat, we did this kind of the treatment. We have a 3 system, OBC onboard computer, TX transmitter, and the CW beacon, and the RX receiver system. We put the small PIC processor, 8-bit PIC processor in each of these 3 systems. And they are working for the management of each subsystem. But in addition to that, they are watching the behavior of the other subsystems. And if the other subsystem fails or hang up, it reset that system. That means cut off the power line and reset it. So that kind of mutual monitoring is a very, very effective way to make the system work normally. And the die-hard system technology is essential. Okay, like a mutual monitoring, reset operation, solar power generation, possibly in any altitude, and the under voltage control and recovery from dead battery situation and so on. So we could obtain this kind of the many technology which can make the satellite die-hard. So please consider this kind of the technology by yourself. Another very important technology for the satellite development is integration. We have many, many areas of the research, but not only one research area, but also many, many research areas should be integrated to develop one satellite, one rocket, one aircraft, and so on. So system is very, very important. System combines many engineering fields with balance to realize reliability and high performance. So this kind of the systems integration is very important. Another very important training is a problem solving. So please put this problem solving in engineering world. From design chart, you can easily analyze or simulate the functions of this system. This is a forward reasoning. This is called the forward reasoning. But the important thing is that backward reasoning. That means from functions, what kind of the design chart will be required. So this is a design task. It is a backward reasoning. So from symptoms, causes, or from result and effect, what kind of the measures and plan will be required, everything is a backward reasoning. So we should make more emphasis of this backward reasoning training. So this is a problem solving training. Okay, from wants to how to realize that. So the satellite development or CANSAT development will have this kind of the features. So I think it's very, very important as a problem solving training. Now, there are full of difficult problems, so many global problems which are mutually related. It is not easy to solve these problems. So we need inverse reasoning or problem solving skills. Okay? And you don't have to solve the problems alone. You can make a friend or you can make a team. Okay? And find out person who have the required skills, knowledge, human network, facility, money, and so on. That is a team. And open innovation would be very important. And the important thing is that these tasks and the mind of problem solving can be trained practically in satellite and the CANSAT project because they have a very big motivation to succeed this kind of the CANSAT or the satellite. So this is a very important problem solving. Let me show the several examples of the problem solving in the CANSAT. So maybe as you know, the CANSAT has been used for the training of the student at the initial phase for the satellite development, project management, systems engineering, and so on. This is a picture in the ALICE experiment. And this ALICE, the United States experiment, started in 1999 when I stayed in Stanford University for 2 months. At that time, we negotiated with Aeropac, amateur rocket group, to lift our CANSAT up to a certain altitude. That was the start of the ALICE. Up till now, we did 22 times of the ALICE up till now. And as you see that the more and more universities from all over the world have been attending this ALICE. So now it became a very big international event. Let me show very interesting competition called the comeback competition. So the rule is very simple. We put some target point on the desert and designated its longitude and latitude in the CANSAT so that the CANSAT autonomously control itself to come back to the target point, and the one which comes nearest to the target point will win the competition. It's very, very simple. And as you see that the flying back type or robo type appeared. And this showed some flybackers like a fixed wing type or parafoil type or robo type. After the landing, cut the parachute, walking back to the target point for example, the 2 kilometer or 3 kilometer. So many types of the CANSAT have been appearing. In 2017, our undergraduate student participated in the CANSAT competition, and they tried to make a 0 meter to the target. And they are first using the GPS. But as you know, that the GPS accuracy is just a 3 meters, so it is impossible to make a 0 meter to the target. So at the time when it comes near to the target, it changed from GPS navigation to the optical camera navigation. But at this point, this CANSAT cannot move anymore. What happened? See? It is a kind of the sunlight is coming from the target direction, and it cannot recognize the target. So, but they have a second chance after 2 days, and they considered and experimented before the second chance, and finally they achieved the 0 meter to the target. So this is really a very good problem solving because they should use only the material which they brought to the desert, okay? And only the 2 days is remaining. So they should consider what they can do within these 2 days and within the resources they brought. So that is a very, very good, problem-solving education. And this, student who trained this, CANSAT is now the main member of our satellite development teams. Failure happens many times. So after the 20 years, failure still occurs, about a 50% failure because technology advanced, but students who are working on the CANSAT is a novice every time. So this kind of failure occurs. What happened? So this is parachute and the main body was separated and the main body crashed on the ground. It happened in 2000. This kind of failure happened. But important thing is that student can learn many things from failure. How to avoid failure, what we should do in order to avoid failure. So, and what kind of the design would be adequate in order to avoid failure and so on. And the important thing, another important thing is that engineers should experience failures while the project size is small. While the project size is small. For example, a person, novice person went into JAXA and he participated in the 300 million satellite project. And because of his mistake, the satellite failed. And he said, oh, this mistake is a very big loss, but I learned a lot from this failure. Is that okay? Maybe it is not good. So the student should learn this kind of failure while the project size is small. So this is one of the very important objectives of the CANSAT. So I have been contributing to the International Space Education Support Program. For example, we created several e-learning tool and hands-on training using a CANSAT educational training, CLTP, and the micro nanosatellite development support, and also we are arranging the launch from ISS. Now, the JAXA is very generous to provide a very cheap or low-cost launch opportunity to the world. So this is called the JQ. We have two categories. One is international collaboration proposal. That is a foreign country will collaborate with a Japanese university to propose one project. And the JAXA, if the JAXA, employed, selected, then you can have a very low-cost launch opportunity. Another one is an innovative mission proposal, but this is for only Japanese university only. So I think this international collaboration proposal would be very, very adequate for you to have a very low-cost launch opportunity from JAXA. So please contact the JAXA. And we have a brochure outside about this project, and so please get one brochure. Okay? Finally, I'd like to show some new wave of space business in the world. As I said, based on the micro nano pico satellite, many type of the new business is appearing all over the world. This is a mega constellation by small satellite. Maybe as you know, that Starlink is now trying to obtain 12,000 satellite constellation in order to obtain the internet in the sky. Altitude is 3, altitude, and already more than 2,000 or more than 3,000 satellites were launched already. So the satellite is about from 100 to 200 kilograms. And also the another feature, this is not related to the micro nano pico satellite, is a transport of men by private sectors. So the NASA has been transported the crew to the ISS by themselves, but now, Crew Dragon, developed by the SpaceX, is now transporting the crew to the ISS. This is a new, very, very new movement. In this way, there are two big game changes in the world. The first one is the small satellite constellation. Second one is the private sectors, especially venture companies, are doing a very active play. And the government will buy their service, not invest the money to the development of satellite rocket, but the government will buy the service from the venture company. So this is a new trend in the world. As to the technologies, maybe as you know that the DX, digitalization or digital transformation is a very important technology because everyone should develop the many type of the satellite within a short time period for the business and so on. And the mass production is appearing like 12,000 or more than 800 or 1,000 and so on. Many satellites will be developed all together. So this is a very, very new movement. How to tackle this kind of the new situation is a very big issue. And the new business has been proposed by the small micro satellite constellation company like SpaceX and the Planet developing the 3U CubeSat with a 3-meter resolution. I think more than 200 satellites were already launched, and maybe 5 hours or 10 hours observation interval would be provided. And the Spire Global has been measuring the GNSS delay, and then it can provide weather-related information and sell that to the NOAA, American Meteorological Institute. So in this way, many companies are developing their own constellation to do a business. So this is a current trend. As to the communication area, as you see that there are many type of the companies appearing. So this is the number of satellite launched until 2029. So many companies are creating the many satellite constellation. So in this way, in the field of the communication, this kind of the mega constellation is now the popular. So we also collaborate with a venture company. As I said, we developed the 13 satellite, and we created a new technology. And we do not something like a close this technology within ourselves. We transfer our technology to the venture company so that this venture company will contribute to the society or get the business. And the money generated in the venture company come back to the university. Then we can do the second step, next step, research and development. So it's a kind of the ecosystem is constructed between the venture company and the university. That is very important. Governmental funding is just a short time period, like 3 years, 5 years, and so on. But in order to continuously develop the satellite or create the technology, we should collaborate with a venture company like this. This is very important. And let me show the several collaboration with a venture company. So this is an IoT satellite. So if you put the several sensors on the ground, if there is no ground infrastructure of the communication, you cannot get the data from these sensors. So if you put a small transmitter to these sensors and send the data into the sky, then when the satellite flies over that area, the satellite can collect the ground information. So this is we call the IoT or store and forward mission. And we successfully are obtaining the 8 milliwatt very small power transmission from ground to the satellite using this Tricom 1R satellite. And based on that technology, we collaborated with Rwanda to develop their first satellite called the RuaSat-1, which was transported to the ISS and deployed from ISS in 2019. And based on this success, we now try to make something like a IoT or store-and-forward network within the Africa or some other country territories. And this 6U CubeSat has been developed in collaboration with a new venture company called ArcEdge Space. 8 PhD candidates from our laboratory started this ArcEdge Space 2 years ago. And now our laboratory and this ArcEdge Space is conducting good collaboration in order to develop many 6U CubeSat to make a constellation. Okay? Axel Space, another venture company starting from our laboratory in 2008, is now targeting to obtain 10 to 20 satellite constellation by 2025 or 6. And with such number, everyday coverage of the world would be possible. So now they have the 5 satellite constellation, and they obtain this kind of the 2.5 meter ground resolution pictures. Another very important satellite is a SAR, synthetic aperture radar. We collaborated with Synspective, that the SAR satellite company, and our university are developing the bus system for them. And the first satellite was launched in 2020, and the third satellite was just launched 1 month ago. And they are also targeting to obtain the 20 to 30 satellite constellation by 2025 to 6. Another satellite company called IQPS, it is starting from the Kyushu University, is developing this kind of very unique SAR satellite. And already they are launching the 2 satellites. Okay, now I'd like to show the world business size. World space industry size is about 360 billion in 2018. The brown part is the governmental space activity. 60% is United States, okay? But other side, the blue one is something like a civil, private industry. And in this area, the satellite rocket constitute a very small portion. So not only developing a satellite or rocket, but also you should focus on the other area, like a service or some component required for service. So this is very important, because if this service area does not go big, then there is no need for the satellite. Then there is no need for the rocket. So this kind of the service industry is very, very important. Please also consider this kind of the areas. And the promising area, business area using micro nano satellite will include remote sensing, but we should be careful about aperture size. We cannot get the high resolution pictures, communication, space science and exploration, in orbit experiment like a microgravity or other experiment, in orbit servicing like a debris mitigation and so on, and education and entertainment. So this is a very, very new area, but I think there is a very big, promising area. And the space manufacturing is appearing like a 3D manufacturing in space. Okay? And we have many, many startups in Japan like this, and the space data technology utilization, obtaining the satellite data, and the satellite infrastructure and usage to develop the satellite, and the space to tourism, transportation is a rocket, and in-orbit servicing, like Astro's case, is trying to make a debris removal, and the space resources. For example, iSpace will launch the first moon lander, lunar lander this year, and so on. And the RED company is in collaboration with our university. So we are collaborating with many, many venture companies like this. The number of the venture company in Japan is now more than 60. So this is until the 2020. So now we have more than 60. And every year, about 180 million US dollars have been invested to this venture company from private funding or governmental funding. So this is the accumulation sum. So every year we have the 180 million US dollars investment. Okay? And one of the very important activity of Japan is launch service. So we only have a big launcher from the government, but a private industry is now developing the small launcher, just a 150 kilogram payload launcher, which will be launched very soon, within this year or early next year from Spaceport Oki. It is also the new launch site developed by this company. So it is a private company launch site and a private company rocket. So this is a new movement in Japan. So in this way, the business is very good. But also, there is another very important task for the space. That is, a space can solve global issues. Maybe as you recognize, global problems on the Earth is getting worse every year, like global warming, wildfire, deforestation, desertification, food and drought, earthquake, and so on. And we should think how the space can solve or contribute to solving this kind of global issues on the Earth. We should think about that. So as I said in my opening remarks, so this is one of the areas which the university community consider how to solve it using the space technology. That is a very, very important thing. Okay, let me summarize my talk. Micro nano satellite can provide low-cost and affordable space asset for various applications. It goes without saying. And our university, University of Tokyo and other Japanese universities are now targeting their applications to constellation and formation flying. There are many this type of the mission appearing in Japan. And the deep space exploration is another very interesting area. Space business is now having a big game change towards from government to private sectors and towards small satellite constellation. This is a very new wave. And the importance of micro nano satellite as educational tool still remains, especially for problem solving training. So the problem solving is very, very important, and even more important in this kind of the world. And the important questions: can space solve global issues? So we, UNICEF Global Community, would like to solve some solution to this question. Okay, that's all. Thank you very much. Thank you, thank you.
Well, thank you very much, Shinichi, for this great talk and summary of state of the art. Well, Japan is a great player in micro nanosite area. The floor is open for questions. I think you can lead.
Do you have some questions? Yeah, we are preparing the mic runner, so. No? Okay. Oh, yeah, one question.
Thank you so much, Professor. That's very great presentation. I have a question about you mentioned that the private launch it will start in this year or next year. Spaceport key.
Spaceport key, yes.
Yeah, is it possible to use? I mean that is it open for international use also because this is important for our the project and my country. Thank you very much.
Yeah, thank you. So you want to contact this company? Oh, yeah, I'd like to give you some point later. Okay? Yeah, yeah, Herman.
I'm Herman Stein from the University of Stellenbosch. One of the problems I think that we have to look out for in the future is these big constellations of satellites going to be launched that will eventually makes it quite difficult for the satellites due to space debris that's going to be generated, collisions, the chance of collisions that's going to increase. What is your thinking about this problem? Because for SpaceX launching now 20,000 satellites in the next couple of years, I think it's huge, and they're not the only
Okay.
planned constellation for future.
Yeah, I think that's a very big issue. And I think I know not only the small satellite, like less than 100 kilograms satellite, but also the big remaining debris would be hazardous. For example, there are many type of the big satellite like 1 ton, 2 ton, and the more than maybe 3 ton rocket upper stage is still remaining in the space. And I calculated, and the probability of generating the debris will be higher for that kind of the big object. And I think it's more important to remove such kind of the big object in space, and then we should consider this kind of the small satellite, the debris removal programs. So I think we should not after that, but we should consider both of these kind of the big issues. And as to the microsatellite case, maybe the minimum thing we should do is to make the satellite not becoming the debris after the lifetime. So we should implement some post mission removal something like equipment like a very big membrane or electric dynamic tether, so that it can go down to the atmosphere after the lifetime. And also we should study about active debris removal technology. And in Japan, one company called Astroscale is now trying to make a business out of this technology. But not only that, but we should make such kind of the company so that many companies try to remove the debris, a very important debris, like including the very big object and so on. So this is my thought now. It's okay? It's time? Yes. Yeah, questions? You have questions?
I have a question, but time too many to think. Okay,
Yeah, let us discuss later.
Okay, we can have one more questions if there is any.
No.
Okay, my question was about responsive space.
Uh-huh.
Now, there is issue of building
Responsive space. Yeah, yeah.
So what do you think about that? I mean, as university community, can we do that?
Yeah, I think we can do that. Responsive space is very important. So suddenly we need to monitor a certain disaster area quickly. In that case, we should develop the satellite very quickly and launch. And on the second day, we can monitor that area and so on. I think not only the satellite, but also the rocket is very important. So we should develop the both of them. Okay?
Okay. Thank you very much, Professor Lancaster.
Thank you very much. Thank you.
Great talk.
Thank you.
Okay. Open the presentation. Okay, now we have seen kind of state of the art in nano micro satellites. Japan is after USA and China, well, maybe technically can be even better. Now we have, new stories taking place also in Turkey, and our second keynote speaker is Tugay Güzel from Plan S Space Technologies. Tugay, he was born in 1989 in Ankara, and then he has also attended Middle East Technical University, Faculty of Engineering, Department of Electrical and Electronics, and he graduated in 2012. In 2019, he successfully completed his MBA in Bilkent University in Business Administration. And of course, from 2012 to 2019, he's been busy with founding his company called Infinia and managing it. And he was also part of personnel managing GUHEM, that's a space center located in Bursa, Aerospace Training Center. His company, Infinia, is a technological product house with electronic assembly and mechanical production capabilities. As a space enthusiast about space, he's been opening a new chapter with Plan S Satellite and Space Technologies Company. He is the co-founder and CEO of Plan S, and they are trying to do what has never dared be done before. He is married with 1 child. In summary, I will say they founded the company. In 6 months, they completed a spacecraft, launched and operated it. Please, Tugay, welcome.
Thank you, Professor Mr. Hello, everyone. Welcome to this beautiful city, first of all. Hello, Nakazuka. Thanks for the great presentation, and thanks for what you have done so far for the space community. We are a newly established Turkish company, Plan S, and we have founded 1 year ago. And on July 2022, we have founded, and with the help of Controlmatic and Infinia, we are a joint venture of 2 companies. So we are now one of the largest private initiatives in the space sector in Turkey. We have working on the space solutions for communications and also Earth observations. In less than 1 year, in May 2022, we have sent our first satellite, Connecta T11, and it's in orbit in 5 months. Since 5 months, and it's now fully operational. And our next satellite will be going on the December 2022, and the next one will be going on in February 2023. So we now have achieved more than 65 people, and at the end of 2022, we will be more than 80 people now. We are planning to have more than 1,000 satellites in 2030. So we are expanding really fast in Turkey. So we are, as I said, one of the largest private initiatives in the space and satellite business in Turkey. And We have the fastest design and manufacturing in the world for the Connecta T11. As Rustam Hoca said, it's actually less than 6 months. And in 6 months, we have designed, developed, manufactured, and assembled, and all the integration tests, and launched the satellite, and it's in the orbit. So we have really good capabilities on the fast design and manufacturing processes, and we have a really experienced, highly capable team designed and managed more than $1 billion projects in the defense and space industry before our company. So we have the in-house technical infrastructures so that we can be dynamic about the prototyping or producing our satellites. We have many different kind of technical infrastructure that I will mention later. And we have a clear growth strategy because we come from the business side before the Planes. We have, as I said, we are a joint venture, so that we are in the business side as well. So satellite Planes is a connectivity part of our other businesses for us. We are constructing our new R&D building, and we are also constructing our new serial production facility in Ankara, in Bilkent Cyber Park, Bilkent University. And we have our own teams for RF and telecoms, systems engineering, software engineering, electronics, mechanics, and also IoT businesses, antenna design, and many other small teams for what we need in the business. Our capabilities and infrastructures are very wide, so that we can fastly produce and test our satellites our own. So we have hot cold cabinet, we have a thermal vacuum chamber in our own facility. Now we have more than 2,000 square meters of place in Ankara, but now we are expanding, and we are building a new, we are constructing a new building, as I mentioned. So now we have one TVAC, and there will be one more at the end of the 2023. And we have our own ground station, and we are expanding it to the world now. And we are sending to another countries our ground stations, so that we can keep connection with our satellites. And we design and develop our own RF and telecommunication systems. In the first one and the second one, we designed our own IoT boards, so that there is a niche technology for us there. And also we have our own assembly line. So because of that, we are really fast about producing the electronic cards, which is one of the key points for the space industry as well, because most of the companies are not eager to produce just one prototypes for the space sector, and that makes the business really slow. When we get some quotations from the other companies, we usually get 12 weeks at least, and it goes up to 48 weeks. But since we have our own assembly line, it's sometimes when we get the PCB, like in 2 or 3 weeks, next week the complete product is ready for use for everybody. So it's really important for us to have the assembly line, so that we can fasten our process really well. And also we have the vibration and tester shaker now. In the first one we don't have, but now we have our own again, so that we use, we can make the tests as well really fast. So we try and see the problem and solve it in like 1 or 2 weeks at most, so that we can be so fast. On the other side, we have really good talents in our house, and while we produce the satellites, we we approach the satellite as a system, as Nakazuka mentioned, because the system itself is really important in here. So it begins with the systems engineering, as we all know here. All the satellite systems are the critical points are the systems engineering. So we have a really good team there coming from the defense sectors, one of the top-notch projects like the tank projects, like the missile projects, ammunition projects. So they have done some systems engineering in the high level. So in the satellites, we bring that know-how here so that we can make the most critical part, we can make the systems part really really works well. So we on the systems part, we work for the ground and user segment and also space segment. We diluted these to two different sections so that we can go into deep in the two sections as well. And also we have the RF and telecommunication systems, and we have our own antenna design team and also communication subsystem design team. And we, as I mentioned, we make our own STRs, TMTCs. We also started to design our own waveform as well. So it's a really complicated area. In the most of the companies get really struggled here, but we have a really good team about here, so that we are capable to make from scratch to the waveform design. Now we are working in-house for all the departments. So on the other hand, we have electronic systems engineering team, and we are producing our own onboard computer and also payload controller boards for the camera systems. And also we have worked for the solar panels with the TÜBİTAK MAM here, and we made a lot of contribution to each other, I suppose. And we have our own electrical power systems as well. And in the first satellite, Connecta T11, we have gathered the flight heritage for our own boards for every part. So it's now working for our own boards and also the antennas and the fully operational, as I mentioned. So we have a flight heritage for our own boards as well. And with the mechanical system, we have a mechanical production line and prototype workshops. We have 3D filaments printers and also CNC machines and freezers, so that as like the electronic component assembly line, we are really fast on the producing of the mechanical part as well. On the other side, we also make the analysis and test equipments for the structures, for the platform itself. On the software engineering, we have many different kind of software departments, because we make the software interface as well and the embedded software as well. So we have 3 different software segments that's working on ground segments, communication softwares, and the satellite mission softwares itself. So we have divided to 3 departments so that we can touch all the software parts of the satellite systems. As I mentioned, we are now constructing our own building. We have just started to build it. Now we have 2,000 square meters in total, but with our new R&D building, we will be expanding to 9,000 square meters, and there will be clean rooms for 10,000 and 100,000 class clean rooms. Sorry about that. So we have test chambers, EMC, EMI laboratories, electronic and mechanical laboratories, and huge office spaces for our team. And also we want to make it as a space hub for the Ankara region in Turkey, because we believe that contributing to each other for the industry players is really important for everybody. So while we are doing our first Connecta T11, we get a lot of help from, for example, Metexan and some other companies, so that giving to each other is really important for us. So on our roadmap, our first satellite is sent at 25th of May, and second one will be going on the December 2022, I suppose 18th of December with the SpaceX Falcon mission, and the next one will be on the February 2023. The second satellite will be about IoT, completely will be about IoT test bench for us, because we will be making IoT constellations and ground observation constellations as well. So for the IoT constellation, it will be our first completely dedicated IoT satellite in the orbit in less than 2 months. And in February 2023, we will be sending our first 6U camera Earth observation satellite in February 2023. So that will be a dedicated mission for our camera mission, and it will be less than 3 meters of GST, and we are working with the Dragonfly for the camera part as well. And after that, next year we are planning to send at least 2 more, but we will be expanding really fast, so I suppose it will come more. And in 2024, we want to send the first IoT constellation phase, and at the end of 2027, we're supposed to have more than 300 satellites in orbit operating. We mainly focus on the 3 areas, which are mostly commonly most of the companies work, but we think that not only one solution will be enough for the future, as the questions that you ask. You have to integrate both solutions together. So you will not be able to solve all problems with the IoT or all problems with the Earth observation, but you will need both of them to solve the real problems. So we work in not only IoT but also Earth observation, and also we give a satellite as a service solutions for our customers. For the IoT part, we plan to have the IoT constellation and starting from 2024. And since Contromatic and Infinia is working in the IoT business as well, we have the connection, we have our customers already in the market. So when we get the connection, the companies, the joint venture companies will be the first customers, so that we will be testing and giving the service to the real cases, so that we are really we have really huge advantage on that part. So on the IoT part, we know the problems from the market. So because we work on that market, so we know the problems, and on the planets we are trying to solve that solution, because one of the biggest problems in the IoT satellite business is the mass connectivity. Most of the companies are not able to get mass connectivity right now, because the satellites are not able to do that for the low cost. But there are, of course, some companies coming from the past, like Iridium or Astrocast. They have satellites in the MEO and GEO, and they are giving that services now, but they are really expensive services compared to the 2G, 3G on the terrestrial side. So what we are trying to do is to connect the terrestrial and satellites together, so that we can get the whole connectivity for the whole areas, all the rural areas, terrestrial areas, all the places, so that you get the connectivity. So when you get the complete connectivity and when you get it to reduce the cost, when you reduce the cost after that, so it is like a new business area, not the satellite IoT business area, not the IoT business area, but in the middle there is a huge portion. So the challenge is the mass connectivity here. So we are trying to solve that problem, like some companies. And on the Earth observation side, as I mentioned, we believe that IoT and Earth observation should be working together so that the real problems can be solved like that, because most of the problems that the Earth, the world now facing are complex problems now. So you cannot just put some sensors and get the data from IoT, and you cannot say that, okay, the problems is solved. The world is now changing really fast, so that you have to adjust yourself to that change. And we see that the Earth observation and IoT together can bring some solutions to the Earth problems. So we mainly focus on these problems, and when you make the IoT and Earth observation, so that you can give service and give the complete solution, so that you can give the satellite as a service solution. So as I mentioned, I'll not make it so long for my presentation, because everybody, I suppose I don't have enough time. But since we know from the markets, our value proposition completely depends on the customer needs and what we have on the market. So what we have on the market is not completely matching the customer needs, because we are at that part we are the customers as well, but we know that some satellite IoT solutions or terrestrial solutions are not competing with the customer needs right now. Because, for example, customers need the low latency, but most of the market offerings now has the really high or medium latency for that part. Or customers need really affordable prices, but on the satellites connectivity, the connections are really expensive, so that most of the companies, even though they need the connectivity, they cannot use the satellite IoT services because of the prices. So as well as these, the continuous access to data is really important, but only 10% of the world's Earth's terrestrial areas are connected with the communication connectivity. So the 90% is still out there, and we cannot touch them. Even though some of them is not needed to connect as we think, but there are many different areas that almost every place needs the connectivity, like the pipelines, like the wind turbines, like the hydroelectric turbines, like the marine industry. So many industry needs the connectivity at least some point. So, but the continuous communication is not achieved right now. So we think that with the satellite LEO business, the newly established business, will solve this problem as well. So as I mentioned, what we mainly focused on is what customer needs on the market, so that we change our approach according to the customer needs. So for example, we want to have the global coverage in 2025 at most, and we will have a low power, low latency data services, and we will have low data prices per devices, and also we will have low hardware cost for the devices, because we need to put some devices to each IoT devices, so it needs to be really low cost. We will have frequently data updates when we have the constellation, and we have an interface right now, so we use on our IoT devices with a user interface, user-friendly interface, so that we can collect the data and show the solution, not only the data but also the solution to the customer. On the IoT part, there are some different methodologies, and what we do is we bring two approaches together, and first we get direct to satellite connectivity, and secondly we get satellite to ground station connectivity. So you cannot make just one. You have to implement all of them together so that you can get the data from every each place. So for the IoT, we have an approach for that. But for the Earth observation, we mainly use the ground station. We will have our ISL systems in the September 2023, I suppose. So all of them is needed with the links in the satellites. And satellite as a service solutions actually connects two different solutions to each other, so that you can connect to different kind of the devices as well. What our revenue model is mainly about the service and giving the service. We first of all, on the IoT side, we are subscribers of the recent satellites now. So we will change our subscriptions to our own satellites at the very beginning, and we will have more subscriptions based on the IoT devices. And also, since we have the global coverage with the same satellites, we have plans to expand to mostly in the Middle East, Africa, and Turkmenistan, Azerbaijan, mostly Turkish governmental places. We are in talk with most of the companies with our businesses on the IoT side and the Infinia and Contromatic sides. So we know that there is a huge market gap there, so that we can go in that business really fast. And we will have some partnerships as the current satellite providers use the partnerships. We will use the partnerships as well, because the business needs it, and we have in talk with some huge companies from Turkey and also from abroad. And also in the long term, like 1 or 2 years, we may think to go into space programs for the different kind of different governments. So because we are now in the moon mission with the Turkish Space Agency, with the Delta V, and maybe later for some other reasons we can go more space programs. We can go into more space programs. So lastly, but the most importantly, our team is really capable of doing this stuff. We have a team of 65 now, but you can see the projection for at the end of the year 81. We are planning to be. Most of our team is coming from the defense sector, is one of the best companies in Turkey, and they have contributed really well in the defense industry before Planes, and they have achieved really hard. They have solved really hard solutions before that. So our the most important aspect is we have a really good team, worked, and we have more than 40% of our people has more than 8 years of experience, and we have a huge team of engineering. Like now, it's 50 people now, and it will be about 64 at the end of this year. So thank you very much for listening. If you have any questions, I'd like to happy to answer. Thank you.
Okay, thank you, Tugay. After, with plenty of capability from academic side, now we have seen a new industrial side, and the floor is open for questions. Please, go ahead.
Please. Not yet. Not yet. Contromatic and Infinia has their customers. They are the companies, they are the joint venture, the sister companies. Planes has not generated any revenue yet because we have just one satellite, but we will be starting gaining revenue at 2024. Yeah. No, we are funding completely privately from Contromatic and Infinia. Yes. You're welcome.
Hi, Shakib Bulgar from the Netherlands. My question is that you said you develop your satellite in 6 months. Could you please be more specific about which subsystems you procured, which subsystems you developing now?
We have procured. We have actually developed all the subsystems as well, but we have procured some of them to check our developed boards. So we got the EPS, OBC, and TMTCs from abroad to check about them, and also one or two more boards. I don't remember really well because of the technical part.
Also ADCS.
Yes, also ADCS. Sorry about that. And I'm not the technical guy anymore. But all the, not the ADCS, but all the other subsystems we also developed in-house and test them in the orbit right now.
Okay, we had Mansur, Kabir, Dr. Mansur, and Dr. Dastan.
Please.
Hi, my name is Ucho from QTech Japan. You said, related to the previous questions, you said that you can build the satellite in 6 months. But can you get a frequency in 6 months?
Yeah, it was the hardest part actually. So at the very beginning, we have applied for the frequency, but we get help from the Turkish Space Agency as well because that's a bureaucratical issue. But since this is a test satellite, it's not that hard for like the commercial satellites. So for the commercial one, it will not take 6 months. I know it will be more, but for the test satellites, there are some points that you can make it faster. Yeah. Here, please. Yeah.
Microphone, please.
Please use microphone.
Actually, Emre is here. Emre is our head of finance and operations. So you can talk later in detail about the ROI, okay?
Okay, any further question?
Okay. Thank you very much for your time. I hope you enjoy your trip in Istanbul. Have a nice day.
Okay, thank you, Tugay, for your talk. We are a bit early, but let me give some programmatic information. Now we have a coffee break. You can have, actually we had also coffee tea early in the morning, but we've forgotten to inform you. So some has benefited, and including myself, most of us has forgotten. Sorry for that. Yes. Just a minute. Okay. And, okay, let's do it. Okay, for the next session, we need your presentations. So I think we need presentation from Samir Lahouar, the Tunisian team. You are here, welcome. So we need your presentation. And one more announcement, the presentation was by Giovanna Ramirez. It will take place tomorrow or the day after. Instead, we have Erdem Onur Özyurt replacing Giovanna Ramirez. And Ms. Nazgül Kaliyeva. Okay, we need also your presentation. Thank you very much. Welcome also. Fine. These two presentations, I have them. I'll give them to you. Okay? Thank you. Okay, so now we are going to have coffee break. Please enjoy it. Then after the coffee break session, we have lunch at the coffee break area. Please take a seat and wait for your lunch. Okay. Well, this is a complete capability development project, as I will going to describe. Actually, currently, it looks like the picture in the middle. The purpose, again, if you have heard in the morning, it's to build a constellation of high-resolution Earth observation system. And that 1 unit CubeSat is still beeping in space, and it's our very first CubeSat from 2009. Some information about B, I will skip that. So where we build our spacecraft, actually, while you are here, if you haven't been there, you are very welcome to visit our lab. It may be during lunch, or I think if you're here tomorrow afternoon, again, during lunch, we can prepare a visit. And currently, we have a 3-unit CubeSat ready for launch. And it will be shipped in 2 weeks. And if you like, you can see it along with our testing facilities. And you can see a photo of the lab. And so far, we have completed 7 CubeSats. And you can see their completed photographs placed around the world on the left side. And we have also ground facilities. It is UHF, VHF, SX. And here, the core team, well, we have many more, since that's the university, we have many more students, but of course, since we are not a company, it is not like Plan S having too many engineers, experienced engineers, and all the infrastructure anyway. But that's a very, very good team. So what is the project? It is to design, develop, and launch with a suitable launch provider. Currently, we are planning to have a launch by the end of next year or early 2024 with Falcon. Since a space system has 3 segments, launch, ground, and space, well, I will spend most of the time on space segment, but we are also building, with the support of industry, a very capable ground station. And it is being built by Profen, and they are also present here. Again, well, the mission is Earth observation with all civilian applications in low Earth orbit. Again, here, to see the details, we are working with Pakistan Air University. Actually, Pakistani people, they have good experience on large spacecraft, mainly commercial communication spacecraft, and some on large Earth observation. Well, of course, now the niche is very capable small satellites, and I think this is also a very challenging project, having 1.5 meters with 8 channels at 500 kilometers. Well, and we have many partners, of course. But in any case, the main purpose is to develop human capacity further in Pakistan, also to increase our capabilities, since this is a new project, and this is very related to SDG 2030 goals. So what are the objectives? the Air University will have its first space asset in orbit, but this is not a simple project, and establish sound infrastructure to communicate with the CubeSat, and then we are going to have a really professional ground station, provide practical knowledge of space technologies to students, so we have many trainings, extend knowledge on cutting-edge miniaturized imagers and their capabilities to contribute to Earth observations. As you will see here, the solution is 1.5 meter PAM plus 7 multispectral from Simera Sense in South Africa. So they are also a partner in that respect. Then we study constellation of CubeSats. And well, of course, there is a very strong basis for international collaboration among project partners, not only partners, and also contributors, as I will show. Then training, knowledge, and technology transfer to Air University. As an academic institution, actually, we share all the information we have. We also see a similar trend in BIRD project, for example. And of course, this is a multidisciplinary and international teamwork. Here you see the work background structure of the project. And with considering the payload, the minimum we can fit, it's a 16U project with about 20-25 kilograms. And that's a limitation considering the budget, so we don't want to go larger and heavier. But you see that it's a complete solution, including launch and ground infrastructure in addition to spacecraft itself. Here you can see the details. So the project is already set. All the partnerships are established. All the subsystems are determined. Preliminary work has already been done. And here you see the partnerships. So the payload provider, the subsystem providers, service providers, ground station providers, and in the center, design development, testing, etc. Here you see the personnel involved. On the Pakistan side, there is a large personnel, but we just present the name of the lead currently. So the aim is to complete, it's also challenging to complete the spacecraft by the end of next year. Well, there are many problems occurring worldwide. Well, so far we've been able to cope with, but we will see how it goes. Here is the concept of operations. So this is a camera spacecraft, similar to some others like planets, for example, or a very capable Canon electric spacecraft, very, very capable, and well, different from then. And then we have, well, TMTC with S-band. This is also challenging, using patch antenna. And again, X-band for downloading 50, 100 megabits per second data. Here you see the payload. It is PAN plus 7 spectral bands from 450 to 900, actually. And the interesting thing with this imager, it has PAN plus 7 bands, and all are 1.5 meter capable. So this has been different based on my knowledge. And when we experience, we will see. Here you see the camera. Currently, we have the structural and electronic function. We have the engineering model of the camera already in Istanbul. So I will skip the specifications. If needed, we can discuss, or you can find it from the web also. But it is, the camera itself is about 12 kilograms. The SWAT is 14 kilometers at 500. Well, of course, there is lifetime issues because, let's say, our partner would like to have it at least 4 to 3 years in orbit. One needs to be careful with that. Here you see we have engineering qualification model, not fully functionally representative, but not fully, let's say, physically. But then it is a kind of, then we say AQM and flight model, but I think the final product is more a proto-flight model in that respect. Here we see the, then the coverage is really critical because our aim is to have daily coverage, and then we need to tilt the camera by 15, 20 degrees. We carry out such analysis. Typically, if you do not tilt, Well, maybe you see the same location every 3 weeks or every month. But if you have 15, 20 degree, up 15, down 20, if it is not one day, in few days, 1 or 2 days, you can get that. And here in the table, we have the analysis. And then power generation is a critical issue, and we are going to have deployable panels, and of course, how to manage the direction of deployable panels regarding the lifetime of the satellite. That's an issue. So we've been trying different configurations supported by analysis. Here you see so these are also different designs. And regarding the data generation, that's also critical. Because we have 128 gigabyte of storage. This is a photo by another camera of the company, 4.7 meters. Actually, this was the ISIS mission, the NAPA-2 mission, and we have a presentation, and you will hear about that presentation by ISIS. This is also our partner. Oh, let's keep. Well, GSD is one thing, but the quality of the picture, like the MTF, signal-to-noise ratio, these are other critical issues. Currently, that's the general design. As you see, it's the camera spacecraft, 2/3 of the volume denoted to camera, and 1/3, and we have a very capable star tracker. And now currently we are using 3 wheels, but probably we are going to use we will need to use a 4-wheel. So that's the design, and here is the ground station. That's a system already produced by Profan company. It is one large dish with both S and X capability. S is 2-way, X is just downlink. So it is an XY pedestal system, and it's a heavy system. We've been studying the link budget. It seems we are doing okay. So the project is in CDR phase and will be launched. Well, we hope to have a launch to complete the spacecraft with all the testing and such. The software development we've started, but it's a very time-taking issue, as was mentioned earlier. We'll see, so 2023 or 2024, that's the purpose. Thank you for listening.
Thank you very much. So, are there any questions from the audience? Please raise your hand. Yeah, okay.
I want to ask about the camera. Is it has a flight heritage? The camera?
Well, it has a flight heritage without result.
Without result. Okay.
It's been in space, but no data.
Okay. Are there any questions?
Hello, Arno Barnard from Stellenbosch University. I saw there in the slides right close to the start, you said the orbit will be close to equatorial. Is that correct?
No, it is SSO orbit.
SSO orbit?
Yes.
Okay, so would there be chance of other ground stations around the world be involved to
Well,
help?
actually, yes. I mean, the SX ground stations are not that cheap, not like the UHF. So we have one here in campus. We are going to use that, and we are going to establishing one in Islamabad. It will be used. And, well, any other interested party, well, with the consent of the Air University, can follow, of course. I mean, with your team, we are always open to collaborate, no problem.
Okay. Are there any other questions? So I'd like to ask, I may miss your presentation, but what is communication speed, downlink speed?
It is 100 megabits per second.
100 megabps
Yes.
for X-band?
For X-band, yeah.
Okay.
For S-band, it is up to 5.
Good. Thank you very much. So in future, you don't consider the, how can I say, application of the laser communication?
Well, yes. We've been doing some preliminary studies, and it's been interesting, but we are not there yet. Yes, we are very much interested. Actually, I think it's been in the portfolio of Planes because we've been discussing all those issues. I think we have to do that, the laser communication. I know that there are some preliminary studies in academic scale, and I am talking to all, and if we can manage something, we will try. Thank you.
Okay, okay, thank you. So are there any questions? One more? No? Okay, so thank you very much. Okay, so let's move on to the second presentation. Mr. Samuel Lahour, please come to the floor. And the title is Space Technology Training and Capacity Building in Tunisia through the FACT project. Okay, and he is from Tunisia. So,
Center for Nano-Satellite Research.
Right? Center for Nano-Satellite Research. Okay, so floor is yours.
Thank you. Good morning. So my name is Samuel Lahour. I'm working as a researcher at the Center for Research in Microelectronics and Nanotechnology in Tunisia. And I'll be talking about today space technologies training and capacity building in Tunisia through the FACT project. The plan of my presentation is as follows. So I'll start with a small overview about the center where I work. Then I'll talk a little bit about research facilities, space-related equipment, CubeSat project that we are working on, and then I'll conclude my presentation. For the people who don't know Tunisia, Tunisia is the country between between Algeria and Libya, and it's almost 2 hours and 30 away from Istanbul. And our center is in the center of Tunisia, where work is mentioned there. And in this center, it's actually it's a new center dedicated to microelectronics and nanotechnology research. It's located at the Technopole of Sousse, and its main objective is research and development in microelectronics, nanotechnology, and applications. And we are trying to work on space technology as applications for microelectronics and nanotechnology. As human research in our center, we are not allowed for now. We are almost 16 professors and 15 students between PhD and masters, but sometimes we get more than that because students, they come to do some projects with us. And then we have almost 17 administration staff members, including 4 engineers and 3 lab technicians. So the micro and nanotechnology services provided by the CRMN. In CRMN we acquired and we are currently acquiring also some high-tech platforms such as CAD, electronic testing, Fab Lab, NanoFab, photonics, nanoscopy, and we are installing these platforms for researchers to do research in this domain. One of the platforms that was currently installed is electronic testing from DC to RF, and it includes network analyzer that can go up to 40 gigahertz, signal generator spectrum analyzers, and also some digital storage oscilloscopes. So, of course, we use this for our work in developing CubeSat projects. Our center currently has 4 main projects that it's working on, and one of them is called the FACT project, and FACT is for fabrication and applications of CubeSats in Tunisia. So it's a 4-year project and started in 2018, and I'll talk a little bit more about this project later. We have also got a Horizon Europe twinning project, which is called PREMINAS, and it will start in the 1st of January 2023. And in this project, we have 3 other partners, from France, Spain, and Germany, but this project is mainly for capacity building in microelectronics and nanotechnology, and it's not very related to space. So here I'll talk about mainly about the FACT project. So some brief history about what we were doing in space-related projects, not in the center, but also in a lab that is collaborating with the center. We participated in many conferences and trainings since 2010. In 2013, UNISEC Tunisia was created. And also we had 2 schools about CubeSat development, 2012 and 2014. But all of these, they were mainly theoretical trainings, and we didn't have any budgets for practical projects. So that's why in 2018 we started the FACT project. As I said, FACT is for fabrication and applications of CubeSats in Tunisia. Initially it was a 3-year project. It was due to end in 2021, but we had a 1-year extension due to COVID. And this project is mainly financed by the Tunisian Ministry of Higher Education and Scientific Research. And it's a collaborative project between our center, an industrial partner which is called Innova Robotics that works mainly on robots development, the National Center for Mapping and Remote Sensing, which is under the authority of the Ministry of Defense, and the Microelectronics Transformation Lab, which is a research lab at the Faculty of Science of Monastir, Tunisia. And this lab provides us with students to work on the different subjects in the project. So the main objective of the FACT project is to start the first university space project about CubeSats in Tunisia, because in Tunisia actually we don't have a space program, so we are starting to have projects in this domain, so to have access to space technology for students in Tunisia. And also from the objective of this project is to develop scientific and technical capacities in space domain, especially in the technology of small satellites. And also we wanted this project to do some application of the CRMN research activities in microelectronics and nanotechnology to space. So the specific objectives of the project first was to acquire the concepts of space technologies. Second was the capacity building of engineering masters and PhD students in emerging technologies. And the third objective was to install CubeSat mounting and testing facilities that can be later on used for collaboration on bigger aerospace projects. Also, one of the objectives was to help in the implementation of new aerospace companies in Tunisia, because where our center is located, the Technopole of Sousse is mainly dedicated to new technology companies. So there are many companies that are being installed there, and we wanted to kind of give a chance to students to have some capacity buildings in aerospace engineering. And last is contribution to reinforce national research and innovation activities related to space technologies. As expected outcomes, we set 5 outcomes for our project. First 3 outcomes are we wanted to install mounting CubeSat mounting facility, so we can later on, if we have other projects, we can easily work on CubeSats. Then we wanted to make a CubeSat testing facility, and the third is to make a CubeSat prototype that later on can be developed into a flight model. The fourth outcome is capacity building, of course, in space domain, and as last outcome, communication, dissemination, and sustainability of the project. The project budget is not a lot. It's around $130,000 for the 3 years of the project, and now they are 4 years. And the main part of this budget is dedicated to equipment, some to mobility, and also training and overhead. The personnel involved in the project, we had different fields of studies, such as electrical engineering, microelectronics, telecommunications, mechanical, geomatics, computer engineering, and information communication technologies. You see in this list, we don't have aerospace engineering since we don't have this specialty in Tunisia yet. So all the people that are working on the project, they come from these fields of studies. I'm myself electrical engineering. So we had 8 researchers, 3 engineers, 8 grad students, and 8 undergrad students. So for the CubeSat mounting facility, we were able to make or to install an ISO 6 class 1000 clean room with 12 square meter area, and it's a modular, transportable hard walls and plexiglass, and has 4 fan filter units to be able to have the class 1000, and of course ESD floor and anti-dust LED lights. So this is the clean room that we ordered, and then we installed, so it's already there. Next, I'll talk about the CubeSat prototype that we are working on. It's one new platform. It's, of course, aluminum structure. It has onboard computer, EPS, ADCS, and UHF communication. And as payload, we are planning to have a software-defined radio payload communication system. So in the rest of my presentation, I'll be talking about small projects that were actually done during the last, I think, 2 years of the project. And these projects, of course, they were done by students, mainly grad and sometimes undergrad students. So the first project is the Attitude acquisition system with wireless data transmission and autonomous power and GUI, graphical user interface. So it's mainly composed of 3-axis magnetometer, gyroscope, and accelerometer, and it has also Wi-Fi data transmission, so we can control the system and send data in real time to the computer. And this way we can analyze the signals, and also we can control later on the system for ADCS control. Second project, in the same ADCS system, we built a Helmholtz gauge for Earth magnetic field simulation. It's a small cage, 45 centimeters cube. It can be used easily for one CubeSat testing. It's aluminum frame, and it can generate a magnetic field strength of plus or minus 120 microtesla on each axis. And in this, we had precise magnetic field control through the graphical user interface on the 3 axes independently. And this system was fabricated in our lab and tested, and it was working perfectly. The third project is the Attitude Determination air-bearing sphere for frictionless rotation. It was 3D printed in our lab and can hold one new CubeSat. So all the projects that you are developing are for one new platform, since we are working on one new platform, and allows frictionless rotation on 3 axes using pressurized air at 6 bars. Also, we have some students that worked on air magnetotorquers with dimensions of 9 millimeter by 9 millimeter and can generate magnetic moment strength of 0.32 amps meter squared, and the power consumption less than watt, and mass of 30 grams. This was designed and made in-house for ADCS testing purposes. So this with the attitude determination system and the Helmholtz gauge can be used to simulate, to measure or to determine the attitude, and then to control it in another project. Next, for the electrical power system projects, we worked also on some small projects, like we have a student that was working on the investigation of variation of the satellite's illumination period while in orbit, and he found that the sunlight period is mainly affected by the satellite's beta angle and altitude, and so these parameters should be carefully selected to minimize the eclipse period and maximize satellite's power productions. And in this project, all simulations were done using in-house developed models, and then also they were tried on commercial software to see the difference between the results. Another project in the power system, in the APS system, are solar panel simulators and battery simulators. So these are power circuits that simulate solar panels and batteries, based for the solar panel based on the temperature and solar radiation and the number of cells, and it respects solar panels IV curves for type of solar panels. So we select the type of solar panel to find the IV curves, and then we use that in our model, and it outputs voltage, current, and power, and this can be used to simulate different illumination scenarios just by software, just by entering the different parameters in the software, and then we can simulate this. And a similar project was done for battery simulators, and it works in two modes, automatically charging and discharging. Also, to be able to test the different subsystems, we designed a small 1U structure. It was 3D printed, and we can put in it either commercial subsystems or in-house made subsystems. For the payload, as I said earlier, the payload is SDR based, and we worked on some projects related to that, like for example the SDR bridge, which is a communication system that takes or receives LoRa signals with some frequency and then translates it to another frequency, and this way we can receive with the same system different LoRa signals and then convert them to a single LoRa signal to be decoded at the user ground station. Other CubeSat-related projects, we have a student that was working on planar meander line antennas for UHF CubeSat communications. This antenna has a small size of 50 millimeter by 80 by 1.6 millimeter. It produces on omnidirectional radiation pattern, so we tested this with simulation, and then also we tested in anechoic chamber, and it can give 1.8 dB gain, and since it's thin, we can embed it underneath the solar panels. Also, we have some students that worked on the CANSAT, Sierra CANSAT prototype, and this prototype was used to measure temperature, humidity, atmospheric pressure, and GPS location, and sends data wirelessly to the ground station while descending. So all of these small projects, they were made by students, and they're all related to the FACT project. Also, in fact, we had...
Sorry, 1 minute, please.
Okay, I'm concluding. We had several trainings. So we had the first Tunisia-China Space Tech workshop that was organized in Sierra Leone. Also, we have some students that participated in UNATI training and trainings with UNOSA and Italian Space Agency, and also trainings with CAST in China. So as a conclusion, so Sierra Leone provides many services in micro and nanotech, including high-tech platforms used for research purposes. And the FACT project is the first project in Tunisia aimed at capacity building in space technology, particularly for CubeSat development. It allows researchers to get familiarized with CubeSat development challenges, and the installed facilities will be used later on for bigger projects and also for national or international cooperations on space-related projects. So I want just to make a small announcement that you will have the first conference on space science, technology, applications, and regulations as part of the FACT project. It will be next week, between 27th and 29th of October, and it can be followed online. More information are in this link, spacestar22crmen.tn. And thank you for listening.
Thank you very much. So restriction of the time, so I'd like to accept one questions. Yeah.
Hi, I'm Jim from the University of Auckland. The simulation circuits that you've created, like for the solar panel and the EPS, are those published? Are they available? Are they sort of open source at the moment?
They're not published yet.
Not published yet?
Yes.
Thank you.
Mm-hmm.
Okay. Thank you very much.
Thank you.
So the next presentation is planned to be made by the Columbia guy, but fortunately we would like to replace that with another one. And the presentation title will be Morphological Approach of False Star Removal and the Camera Motion Estimation for Star Sensors. And this paper will be presented by Mr. Eden Anur Azurat from ITU. Okay? So, floor is yours.
Wait, that's okay.
With a full screen.
Okay, go ahead.
Okay. Hello, I am Erdem Onur Özgürt from Space System Design and Test Laboratory. I'm actually a PhD student advised by Professor Rüstem Aslan. Today I'm going to talk about a morphological approach of post-star removal and camera motion estimation for star sensors. Actually, this is a denoising algorithm. I serve as an algorithm developer in this task. This presentation includes the following chapters. I'll briefly, very briefly, talk about star sensors and noise sources encountered in star sensors and the methodology I have developed. And then I will show how a noise injection is done, and then a case study will be illustrated. And the benefits of the algorithm will be shown, and a future work will also be presented. As you know, the commencement of space age in the 60s may allow humans to make giant leaps, and as time elapses and the projects evolve into more complex forms, a need for high accuracy is raised, and so the sensors for use attitude determination in the satellites became more important. Among the sensors, types of sensors, star sensors comes up with accuracy and independence properties. They ensures the highest accuracy, and independence means here independence from location. It can be implemented at any point in space. On the other hand, complexity and cost are some issues. A star sensor flowchart is simply after acquisition of star image, a star detection and centroiding is done, and then a star identification algorithm is implemented to match the observation vector or observation image with the star catalog, and then attitude estimation can be retrieved. Actually, we have 3 basic steps. And types of noises in star images can be classified into false star, shifting star, or missing star. Also, magnitude noise can be involved in this. And also, of course, there is a constant background noise, a white noise in the images. The methodology, the aim of the methodology is simply removing a false star, a potential false star in the image. But when removing the false star, also we have an advantage. We can, in the algorithm, estimate the camera motion, the rotation and translational motion of the camera. This is done by a morphological approach by matching the star pairs, having some features, morphological features of the stars in each star image, and at least 2 consecutive images are needed to implement the algorithm. Here, in a simple way, the morphological features are shown. In the first picture, star picture, there are 4 objects. The ABC objects are considered to be stars, and X object is non-stellar object. So we have average magnitude of star pairs and angular separation between star pairs measured by pixel, and the slope of the angular separation with the image horizon. So we have a vector for each pairs of stars in every image, in each image. And the number of vectors in each image, if we have n objects in it, can be calculated by the L notation. And after having the feature vectors for each pair of stars in an image, we are able to arrange a disparity list from 2 consecutive images by subtracting each feature vector in the disparity list. For example, we have the DAB vector. We will subtract DAB vector from D1, D3, D5, and we will have this disparity list. So if we have L1 and L2 number of feature vectors in two consecutive images, we will have L1 by multiplied by L2 vectors in the disparity list. And then after we have the disparity list, we check if the elements, the first two elements in the disparity list satisfies a tolerance, epsilon A and epsilon D. So the elements, the objects satisfying these tolerances are considered to be star objects. And then a verification step is done by the star objects are assumed to be accumulated within a region of S. If this the difference between the third element of the disparity list and the S are accumulated within an EM epsilon M tolerance, then we verify that these are the star objects. And also by verifying this, we have the rotational motion parameters dynamically. And having the inverse tangent, we have rotational estimation. And after reverse rotating second image, we can calculate the translational motion also. This is how we inject noise. The left-hand side image is without noise, and the right-hand side is the noise-aided image. Here, both positional and magnitude noise are injected. In this project, Hipparcos catalog is used, and in this noise injection image, the parameters are given. Also, the CubeStar sensor is used in this project for the simulation purposes. This is the star sensor used in Sharjah Sat-1 project in close collaboration with Space System Design and Test Laboratory. Also, Hipparcos star catalog is used. This is a case study using the sensor model and the catalog. There are 7 objects here. The second one is the rotated form of the first one. It is rotated by 10 degrees in counterclockwise and translated by 5 degrees in declination, and not translated in right ascension. So also algorithmic parameters are epsilon A for magnitude is 10 pixel in intensities, and epsilon D is for 3 pixels. The outputs are given as non-stellar objects is successfully detected, and stellar objects are matched in pairs. Also, we have estimated the rotation and translation. The true value is 10 degrees in rotation, and the estimation is given. Also, the translational estimation is close to the true value. This is actually a pre-processing stage of the my main algorithm in the PhD thesis. We have also developed a star identification algorithm, a lost in space star identification algorithm. The benefits of this denoising algorithm is removing false stars. But when removing false stars, we also have a previous information for the star identification algorithm. So we can evolve this lost in space identification algorithm into a recursive star identification algorithm with the mean and standard deviation, rotation and translation estimation parameters we have. The dictionary-based lost in space algorithm is not a morphological algorithm. It is a pattern recognition algorithm. It is dictionary-based. It is also based on a regression analysis. Firstly, the nearest neighbor algorithm is implemented to have the most significant vector in the dictionary, and then a dictionary is set up, and then this dictionary is used for making a regression analysis to have the estimation. The regression analysis is simply the lasso calculation. It is least absolute shrinkage and selection operator using a least mean square error. In this, the feature vectors are obtained by using all stars in the image. We have only one object. This is the single object obtained from the all star images in the image. So we have in the database, we don't have all the stars, information of all stars, but only the single image, the information of the single image, which are a number of stars, mean magnitude, and the polar radii and polar angles of the single object. These are some examples from the Hipparcos catalog. The red dot is the single object, and the green text are the feature vector elements. By using an overlap rate, we retrieve the feature vectors for each single image in the all database catalog.
So 1 minute, please. 1 minute.
Okay. And this is how the lasso algorithm is implemented. So what we are doing is here, we use the state transition model, actually the motion estimation parameters, to feedback the dictionary-based matching. And we can convert the lost in space algorithm into a motion recursive algorithm by this way. Here the advantage given is in dictionary-based matching we search for the whole database catalog, but now if we use the motion estimation parameters, we will shrink the region in the database, so we can accelerate the algorithm. Here also we have implemented experiments in the lost in space algorithm. We have already have these results. For example, this is for the normal vector of the camera plane. For example, this graphic shows us in the 99.5% overlap rate, about 8% of the 1,700 test vectors are achieved successfully under 1.2 pixels, degrees, sorry. So, thank you for your attention. This is it. I can have your questions if you have.
Okay, thank you very much. So, are there any questions from the audience? Yeah, please.
Yeah.
Did you have a chance to try your algorithm with real star images? If not, do you expect any difference compared to simulation results?
I haven't tried in real images, but in case of real images, I'm not sure. I expect some deviations. But I need to try it.
Okay. Okay. Are there one more questions? So, yeah, I'd like to ask a question. So, in Japan, there is some researchers who are trying to utilize machine learning technology, like deep learning, for the identification of the star. How do you think about this?
Which technology?
Yeah, deep learning.
Deep learning.
Deep learning, yeah.
Yeah, this is also a kind of pattern recognition algorithm. Well, at first I planned to use them, but this regression analysis actually serve as a first I make a coarse identification, a more general identification, and then I make fine tuning, fine setting in the algorithm, and that makes a two-step into the achievement. So maybe a deep learning algorithm can be integrated into this regression analysis, because I have also combined these two algorithms in my master thesis. Also in future I can also make it possible.
Okay. Thank you very much. Thank you.
Thank you.
Okay, so now let's move on to the last presentation. The title is Some Algorithms for Controlling the Motion of Satellites in a Formation. And this paper will be presented by Dr. Nagzil Kaliev from Kazakh National, Al-Farabi Kazakh National University from Kazakhstan. So, floor is yours.
Thank you. Dear participants of the symposium, I present to your attention a presentation on the theme, Some Algorithms for Controlling the Motion Satellites in a Formation. At present, many researchers prefer to consider the satellite formation instead of single satellites for the problem of space exploration. With the help of the formation, it's possible to solve all class of new problems that are impossible to solve with one satellite. The possibilities of using the satellite formation of the problems of astronomical observations, stereographic survey of the Earth's surface, remote sensing of the Earth in real time are interesting. The object of research, control system of space formation, purpose of the research, to develop a control system capable of maintaining the required configuration of the spacecraft formation for the purposes of the ongoing mission, taking into account the uncertainties caused by external influence. The formation is a system of four, in our case, the formation is a system of four spacecraft forming a tetrahedron or regular pyramid. In this case, the main spacecraft is located above the three accompanying spacecraft located in the plane of the tetrahedron base and moves in an orbit called the reference orbit. The accompanying spacecrafts form a regular triangle, and the head of the tetrahedron passes through the center of this triangle. Let's derive the differential equations of the motion of one of the satellites in the formation relative to the reference satellite in the Earth's orbit. To do this, we denote the satellites, we consider the satellite as B and the reference satellite as A. Let's introduce the coordinate systems shown in figure. O X, Y, Z inertial coordinate systems, the center of which is located at the Earth's center of mass. The OZ axis is directed along the Earth's rotation axis. The OX is directed to the point of spring equinox. AXYZ, local vertical, local horizontal coordinate system. The center is in the reference satellite. The IX axis is directed along the radius vector of the reference satellite from the center of the Earth. The AZ axis is normal to the orbit plane in the direction of the orbital momentum. The AY axis completes the system to the right. Mathematical model of the spacecraft formation motion was developed in the case of an unperturbed reference orbit based on the Sedgwick-Schweigert model. For satellites in geostationary orbit, it's necessary to take into account the influence of gravitational disturbances caused by the inhomogeneity of the Earth's gravitational field. To consider the influence of the figure of the Earth on the satellite in the formation relative motion, describe these equations. We obtain a perturbing function. To do this, we introduce the influence of the second zonal harmonic G2 into the gravitational potential. In this case, the equations of the relative motion of satellite in a formation taking into account the figure of the Earth will take this form. Let's write the equations for the controlled motion of a satellite in a formation in the form 1, where Fx, Fy, Fz are the forces caused by G2. Ux, Uy, Uz are control forces produced by actuators, in our case, control forces produced by thrusters. In this work, we assumed control force as a linear function, as here. To determine the unknown feedback coefficients for the control acceleration, we apply two methods. First method is the root method. That's based on locating roots of characteristic equations of the system in the spatial areas of complex plane. Let's consider the algorithm for determining the control U, based on optimizing the location of the characteristic equation roots. Characteristic equation of this system can be considered independently, and two characteristic equations are obtained for them. Using the parameters of the reference unperturbed orbit of the main satellite in the form, the radius of the circular orbit is 42,000 kilometers. For the root locus method, we obtain the following control coefficients. To form a control acceleration with feedback U in the equations of motion, it's decided to use a linear quadratic controller, which is obtained by minimizing the quality criterion of the form. In this case, the control acceleration U obtained as a result of minimizing the quality criterion has the form 2. In this case, the control acceleration obtained as a result of minimizing the quality criterion has a form, that last equation. As a result, the matrix of feedback coefficients is determined using the LQR method. You can see. To check the obtained coefficients, it's determined using the LQR method. To check the obtained coefficients, we will carry out a numerical solution of equation 1 under the initial conditions that determine the location of 4 satellites relative to the geometric center. The results of numerical studies are shown in this figure. As the required position of the satellites in a formation xt, yt, zt, we set the initial conditions, and obtain this result. In this research, the volume of the formation was obtained as a main quality factor of configuration stability only for short time period. The results of numerical studies are shown in this figure. This result shows that the configuration of the satellites changes under the influence of external forces, which takes into account the shape of the Earth and approaches the initial one with some periodicity. For keeping the configuration for a long period requires the introduction of a control action. For example, maximum increase of the formation volume is observed at half circle at 45-50,000 seconds. In this case, the volume of formation is about 5 cubic meters, which makes it impossible to complete the mission. These figures, AB, illustrates the change in the volume of the formation configuration, which already takes on sufficiently large values already at 1,000 seconds. Over time, the change becomes more pronounced. These figures show the result of changing the volume of the configuration with 2 control methods, root locus method and linear quadratic control method. At one time interval, they show that the effect of external forces caused by the shape of the Earth is leveled at the initial stage of motion, and the entire subsequent period of time, the formation volume remains within the required values. At the same time, it's observed that the control action based on LQR makes it possible to achieve the required position of the satellites in a configuration with a smaller overshoot compared to root locus method. These figures characterizing the change of the volume of the formation over a long period of time, up to 3 days, allow us to conclude that the developed algorithms for controlling the motion of satellite in a formation ensure that the formation configuration is maintained over a long period of time. Accuracy of mutual position of satellites information is equal 1 micrometer approximately. The maximum control force needed to keep the configuration of satellites information is 0.004 Newton or 4 millinewtons. Concerning the commercially available electronic propulsion system, for example, the electrostatic gridded ion thrusters and Hall thrusters with input power up to 200 watts, has a specific impulse varies from 1,300 seconds to 3,000 seconds. That means that maximum generated thrust is about 0.15 Newton or 15 millinewtons. And minimum generated thrust is about 6.6 millinewtons. Comparing the obtained value of thrust with the value of maximum control force of 4 millinewtons, to keep the satellite configuration, we can assume that the developed mathematical apparatus within the framework of this paper can be implemented on control system of the satellite formation in geostationary orbit for controlling the motion of satellites in the formation and their relative positions. In this study, the following results were obtained. A mathematical model of the spacecraft formation motion in the case of unperturbed reference orbit based on the Sedgwick-Schweigert model was developed. Second, numerical solutions of the nonlinear equations of motion of the spacecraft formation, taking into account the figure of the Earth in the case of an unperturbed reference orbit was obtained, and algorithms for formation configuration control relative to the unperturbed reference orbit based on feedback methods were developed. Thank you for your attention.
Okay, thank you very much. So are there any questions from the audience? Okay, so the right behind.
So the orbit is unperturbed, right? When you model it in your equations?
Orbit of formation is a geostationary orbit.
So what causes the shape of the formation to break if there is no perturbation? Is there something happening that causes this? I'm just trying to understand. Yeah. So why does your formation in your model, why does it break? What causes for the formation to break in the model? Maybe I didn't understand the problem properly, but when you presented in maybe page 13 or 14 of your presentation, can you go to page maybe 12 or something? All the way back.
This?
Just back once more. Yeah, there. So it looks like that the formation, a tetrahedral configuration, is breaking after a certain amount of time.
Yes.
So what causes for the formation?
Perturbations from the Earth's inhomogeneity. The distance between spacecraft's informations increase, and our aim to develop control which keeps the distance between spacecraft's information approximately 1 meter in 1 meter.
Can I ask a very quick follow-up? So do you think it's possible to include some kind of an aerodynamic drag in this kind of a model?
Aerodynamic drag, you mean?
Yeah.
This formation located in geostationary orbit, and the influence of aerodynamic drag is very small compared with the gravitational field's influence. Thank you.
But anyway, so it's a very important questions and answers. So please continue the discussion after this session. Okay? Thank you very much. Okay, thank you very much. Now I'd like to conclude the morning session. And some logistic announcement?
Yes. Now we are going to have lunch in the coffee break area. I think we should have the table set up. However, sorry, we have typically internet in our campus is automatic. That's why we have kind of missed the fact that you may not be able to connect. Actually, you can directly connect to the ITU Misafir, that is ITU guest.